Super. Things start working. So we are on the section 5. We need to derive time-dependent Schrodinger equation, and if something goes wrong, here is the recording in the blue frame. So I'm going to briefly tell what are we going to do next Friday. So here is a portion of a text from Squirrels that it was among recommended books, like number 3 and number 4. So it's problems and solutions, and at the beginning of each chapter they give a brief summary of the most important material. So these postulates are summary of the philosophical principles behind not only physical chemistry but any quantum theory, and all things that we will be doing in the rest of the course will be based on these fundamentals. And they're not so much mathematical. They are a bridge between philosophical concepts and math. It was quite an effort of the humankind to develop these formulations, and the formulations here are not, they're not like a creed to memorize word by word. They are more like concepts. And if you look into Wikipedia or some other sources, you will find something different. So it's just a short summary. And I would like to make, on one hand, my life easier to present less, on another, to give you a chance to present and get credit towards your I wanted to say degree, final grade. So about 5 minutes presentation on one of the subjects. And there will be not too many new ideas. We partially discussed it. We will discuss it in the remaining 3 meetings before it will be time. And it is very, very easy to find in basically any textbook that has the word quantum in it, and in Wikipedia as well. So just look through and decide what is most comfortable for you. Okay, so here is the table that you will see on the online. Let me quickly check. Okay, Spencer, thank you for making your choice. And thank you for making your second choice. Okay. We have at least one confirmed speaker, and I do see that a couple of people place their markers in front of second postulate and in front of the fourth. So it means that there is an active thinking. Okay. So here is the link in our slides. And before we go to the actual class material, I'll bring back the faces later. So here are some Nobel Prize awards at the beginning of the 20th century, and those are awards in physics, but we are in physical chemistry, so it's quite legitimate to discuss them. And you have seen that this Duke Louis de Broglie is designer of idea that electron is awake, or at least a supporter of this way. You can skip Raman because it's more experimental, and then you'll see these names of Heisenberg, Schrödinger, Dirac through the course. So Erwin Schrödinger did provide very convenient form to practically solve a lot of problems. Like Heisenberg also provided it, but it's mathematically heavy, and the Schrödinger formulation of this wave theory of quanta is really popular and is being used quite actively in like 90 years since his award, and it was designed in 1926-27. So I'm pointing your attention on Erwin Schrödinger also to here is a little copy paste from the preface of his book. It's not actually the book; it's a collection of the papers, and I will not go through this text because we are limited in time. But if you look through it, it's quite an amusing reading, and it complements what we discuss in the class. So it makes connection between microscopical motion along the path and wavy nature of particles and how they are connected. And the things that we will go over in during the class are kind of summarized here. So if someone stops you on the street and asks what is quantum theory is, you can borrow some words from one of the developers of the theory. And we will come to this concept of eigenvalues in German, proper values. It was maybe not the best translation into English in very soon, next week. And here is the list of few problems that can be solved exactly, that I was promising to mention last time. Erwin Schroedinger does it instead of me. Oscillator, motion of charged particles around each other, rotator. So it's okay. What have we done last time? We went through Euler equation, and I hope that no one had problems with it. I'm not going to design any homework or exercise, just hoping that it's quite simple, and we will use assuming that it's fine for you to use this stuff. Then the broad wave of accumulation of action along the path and serving as an argument, as an angle for imaginary exponential. And then the Feynman, also Nobel Prize holder, equation for propagating wave function that is defined everywhere in space at initial time into wave function defined everywhere in space after certain time, making this propagation, accumulation of action in each point of space, and as a swirl of many trajectories from each to each point, accumulating so many phases and then giving this constructive interference. But this is correct. This is really great formula connecting microscopic trajectories and quantum description, but it is too much for the start, and it is not computationally efficient. There is a way of Schroedinger equation that he got. Equation that the best tool to describe most of quantum problems, and in today's meeting we are going to derive Schroedinger equation based on the this Feynman formulation of quantum mechanics. If you were taking calculus and or did some basic derivatives in high school, it will be not a problem. Just one line derivation. And then I'll briefly chat about so-called commutators. So here is the last slide of the previous meeting. So we are going from wave function in the past to the wave function in the future, and we can chop it onto infinitesimal time intervals. And in each time interval, we change it a bit, and we have a way to describe it. So it's so-called evolution operator, and in each point of space, we have accumulation of phase and motion along complex plane. Okay, so what are we going to do today? I don't know how to spread this 2 lines of derivation onto 50 minutes, or even if it's on the 30 left. It's really simple. So let me check if anyone has problems with the top line. First, so does it seem natural? Does it seem logical after the previous line? So function of position and time, time is fixed. Function of time only, function of position and time, right? And I'll just briefly check if anyone on the remote connection has. Okay, if there are questions, it's much more preferred if you speak. It will save me effort in checking chat line. Okay, no questions. I assume that everyone admits, accepts, and supports the top equation. Now, let's practice really simple calculus. Consider this product of two functions of time and applying time derivative. Why do we need time derivative? Because we want to open a door, open new wave, new approach to efficient description of time propagation, how things change in time by small time intervals, by infinitesimals. So we need to see how things change in time. Therefore, we practice derivative. So let's just take derivative of this function generally. So if you have product of function 1, function 2, how do we take this derivative? How do you call this rule?
So we're just doing the product rule at the top?
Product rule?
No, what that is?
Probably just product rule. It's so natural that often people just do it without giving a specific name. Okay, so we apply derivative to the first function in the product and keep second unchanged, and then we keep first unchanged and apply derivative to the second. So psi t u t psi t d dt psi t d dt u times psi unchanged plus u times d dt psi t. So since the wave function at initial time has t not fixed, so it's not quite a function. It's just a snapshot that does not obey any variation. So since t naught is a constant, we can set this derivative equals 0, and then it will be only the first term. So we practice derivative only over the evolution operator and change wave function and keep wave function unchanged. Now the evolution operator. So we can be very rigorous. H bar integral t not t h t dt. But if we are speaking about short times, it is we can take it as e minus I h bar h of t times let's see t minus t naught So if we integrate over a very short time interval, then instead of integral, we just replace it by product rule. And then if we want to take derivative of this little piece, then I don't know if we can write it in this little corner, but derivative of exponential dt e minus h bar h t, you give the all constants come to the front. Oh, it should be h bar. Then capital H for Hamiltonian, and then derivative of exponential is exponential itself. E minus I, whatever is here in the power of the exponential. So by taking derivative of the evolution operator, we are bringing the constants and operator of total energy and total energy to the front, and then we have the evolution operator unchanged. Make sense? I'm trying to type this little thing again and again each time, and do not concentrate your eyes in one or two slides. I will have this typed in a better form. You don't need to enjoy my precious calligraphy. So after taking derivative, so two consequences, two conclusions from our little mathematical exercise that I think you admit was very short and quite clear. So first, upon practicing derivative, we do not change anything to the wave function. So time derivative of the wave function does have wave function itself. Oh. I'm just running in front of my own voice. I need to slow down a little bit. Okay. So here is the last equation that we derived together. And now I'm going to plug it into here. And then we get time derivative of wave function of t is minus I h bar total operator, evolution, energy operator, evolution operator, and then wave function at t0. Very good. And at this point of time, so the evolution operator propagates wave function from t0 to time t. Yes, here's the missing step that I assumed already completed by. I need to bring it up explicitly. So through derivative, we push forward the constants in total energy, and the evolution operator stays unchanged. But then we can focus our attention on the evolution operator and wave function of the past, and replace it by the wave function of the future, or the current time. And then after this step, on the left we have time derivative of wave function of the present, and on the right we have constants, total energy, and wave function over the present. Which means after applying time derivative to the wave function, we get the same, the wave function itself, multiplied by some constants and total energy. If you admit this derivation, or if you can imagine designing this derivation yourself, you are worth of Nobel Prize at the beginning of the 20th century. So basically, this is the main equation of quantum theory, and if you agree with it, the rest of the course will be just application of this equation to different practical aspects in a narrow sense. Well, we are not done with the course, but it is like the main cornerstone, and all it's not all my mumbling and maybe boring for you philosophical discussions in the previous 4 meetings were just preparation to get agreement to arrive to this equation. So this equation was coming from assuming the concept that electron is a wave. The wave is corresponding to accumulation of action along trajectory, and this action along the trajectory gives phase of the wave function. As soon as we come to this idea, we make just one simple derivation, and then we do have the equation that allows to find wave function. Also, in the meeting number 2, we discussed wave equation, right? Second derivative over time on left, second derivative over space on the right. And they equal this some proportionality coefficient. Nothing was wrong, but the wave equation is not for quantum quantized electron. It is for electromagnetic waves, for waves in musical instrument, acoustic guitar strings. Just by its nature, electronic waves obey an equation that has first derivative instead of second, and it has imaginary unit. Without these tricks, it would be not possible to do correct description. The total energy here will include second derivative over space. So it will be very similar to wave equation. But on the left side, instead of second derivative, which is just the first derivative. Very good, very good. So, do you think this equation is simple enough? So it's called time-dependent Schroedinger equation because it shows propagation in time, and because it was designed by Schroedinger. And it is not the easiest one. There is a simplification of this equation. Like right now there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 letters. Too much. There is a simpler version with only 5 symbols, time-independent Schroedinger equation, and some abridged, shorter versions of the similar course start with time-independent and even do not mention time-dependent. So one can do some very, very basic discussions even with simplified version of this equation. Just giving you a heads up. And there are two versions of this equation: time-dependent, time-independent. Okay. What else? Okay, here's the little comment that is not as important. Let me just bring it up. You don't need to concentrate. Orange or yellow level of alert, not the red. So if we let me check. Did you ever practice derivative in finite differences? I think yes. Maybe not. It's just replacing this calculus symbols with little infinite finite size increments of the function and argument. If you were doing some labs with when one needs to find a slope of a function, then you are doing derivative in finite differences. Make sense? You find 2 points, look for the increment of the function and argument, and find their ratio. Right? So if you want to sound sophisticated, you can tell it, I'm doing differentiation in finite differences. Looks a little better. But basically finding a slope. Now, can we do a slope here over time? And by the functional form, if you were doing or you'll be doing some chemical kinetics, it looks like zero slope direction. So, definition of derivative. Function. Yeah, it's difference of function at future, near future minus function of the present. And I would put this one first, this one second, but to mitigate it, there is a minus. I think last year I was just calling people from the audience, but now it will be not fair because those who are online cannot come. So this is replacement of time derivative, right? And we can place it to the left of this equation. Now, after doing so, we can multiply left and right part by this time increment. And then on the left, we will have difference of the near future and present. And on the right, we will have this constants, total energy, wave function, and time increment. Right? There is no discovery, it just follows from the shape of the equation. And now let's move, so this little bluish circle, let's move the wave function of the present to the right. Now, what do we see? Wave function of the near future is equals to the wave function of the present minus constants, total energy, wave function of the present times increment of time. Right? So if one wants to predict what would happen to the electron in the near future, one can take wave function and practice. And this is a replacement of the Feynman formula that we were looking at. So in some sense, it shows how to get from the present to the near future. Let me see. Okay, I was already typing it before. So it's just the same equation. And here in the yellow box, here let's put this psi out of brackets. Okay? Then in the brackets, we have 1 minus this constant, imaginary unit Planck constant, total energy delta T. How should I interpret it? How should I correlate it with the previously derived final equation where we had in this place evolution operator equals to the E minus I H bar H delta T. Is there any connection between this evolution exponential and this little time increment? The formulation of the question suggests that the answer is yes. And if you carefully look on the board, it has the answer. Or I can hide it. Did your calculus class include series? So what is the series for Taylor series, right?
Yeah.
So what is the expansion of exponential function in the vicinity of 0? Come on.
I can't remember. That's something like.
I'll hide it. Please, please write it down in your books or read it in your notebooks.
Are you talking about the Taylor series for e to the x?
Yes, yes.
So it's x to the n over n factorial
Yes, and
from 0, n equals 0 to infinity.
absolutely correct. And can you dictate what would happen if you practice it, if you just plug in first couple of terms, n equals 0, n equals 1, n equals 2?
Well, it would start converging to a certain value.
So
It's a telescoping series.
August is suggesting that e to the power x equals summation. N goes from 0 to infinity, x to the power n divided by n factorial, right?
Mm-hmm. Yep.
Now, if we plug n equals 0, what would happen?
Well,
0 factorial is 1.
Mm-hmm.
X to the power 0 is
0.
no.
Oh, 1. Sorry.
1. So for n equals 0, we have 1 right here. What are we going to get for n equals 1? In the numerator, x to the first power will be 1. In the denominator, 1 factorial will be 1. So it will be x. And then it will be x squared over 2, then x cubed over 6. Right? Let me. Yes, super. Yeah. So what if we plug in, instead of x, we use this minus I over h bar h capital delta t. First zeroth term will be still 1. First term will be just everything that we have as a power of exponential. Look here. So basically, we re-derived the Feynman formula in a sense that it has been expanded in Taylor series, which is fine if the argument is small. If the delta t is really small, then we can replace this accumulation of exponential phase with this Taylor series. Make sense? Okay, what else can we do? Chronometer. Okay, so one more concept. It is absolutely, it's quite simple at the beginning, but it is important. It will be more and more important this time. So the concept of weight was known before quantum theory. Concept of trajectories, concept of derivatives, everything was in the community. But concept of commutation was not as much, was known for mathematicians who deal with matrices, but was very far away from the focus of chemists and physicists. And here I will slowly start and then pedal to the metal. If we need to multiply two numbers, 1 and 2, or let's be more complicated, 2 and 3, result is 6. Right? What if you swap the order? If you multiply 3 by 2, the same, right? If we are speaking about like concentrations of reactants in the reaction, and we need to multiply them for some reason, if you swap the order, nothing changes, right? If you multiply like strengths of electric field in physics by dipole, which is like how polar molecules are polarizing in electric field, it doesn't matter the order how we mention them, right? And it looks a little crazy to check the order, but from now on we will need to set up rules to formulate total energy on the quantum language. And total energy is like kinetic energy, potential energy, right? And sometimes when we formulate this energy operator, we need to multiply physical quantities. And we do need to care about their order. If you do not care about the order of things in quantum theory, we will pay big penalty. And it is a very new concept, which was taken with a lot of skepticism at the beginning of the theory, and now we just need to come over this barrier. So, it's an exercise. I hope there will be empty slide, and then I will be practicing. So I'm going to practice or just verbalize a little exercise, and it will deal exactly with the same level of complexity or even smaller as we did 20 minutes ago. I just consider as mathematical experiment product of two functions, x and psi function of x. And then I apply derivative over space into the product of these two functions. Please try to do it in your notebooks. You will do it quicker than I will flip the slides. Dx psi. Then I need to practice, not tx, ddx of x times psi plus x dx psi, right? And derivative of x over x equals 1, correct? 1. So dx x psi equals 1 times psi.
Would that whole side just be psi?
Yeah. Plus x dx psi. So now I'm going to move the rightmost thing to the left part of the equation. And when I move it, I just need to flip the sign. So dx x psi minus x ddx psi equals psi. So please catch me lying if you can, or confirm that you believe that it is truth. So if you have any suspicion about this simple derivation, speak now or stay silent forever. A joke. So no one has objections against the lower line. It seems quite natural. Now, look at me. I'm not going to lie. I'm just doing very simple and pure things. I will remove psi out of brackets everywhere on the left and right part. And then on the left, it will be ddx x minus x ddx equals 1, right? So here is the connection. We will derive it very, very soon, or at least introduce that very important quantity of momentum or velocity when we convert it from the language of classical mechanics to the language of quantum theory is replaced to derivative over space. So dx, just derivative, is operator of velocity. I'm a little bit lying. It is not velocity, it's momentum. I need to put some constants in the front, but in essence, it is just derivative over space. And x will be just operator of position. And if you swap the order of this operator of momentum, operator of position, and we here is position first, momentum second, then there is a price for it. Swapping of these things is not innocent. And it comes from the basic math. So when one is talking about swapping the order of any quantities in quantum theory, one needs to be very, very careful. It's not, I'm telling the word penalty, but maybe it's not penalty, maybe it's benefit, but it's not zero. So there is either price or reward for swapping the order. Okay. And we removed wave function and left only things that multiply on it from the first. And it looks quite similar to our time-dependent Schrodinger equation. We have some like total energy, which can be considered like operator, acting on the function. And we remove the function. Now we do just some properties of operators. For a shorthand notation, and all the theories are done by humans for humans, and humans are naturally lazy. To write less symbols, this subtraction of the swap order is often replaced by this rectangular bracket. Like dtx comma x in rectangular bracket is equivalent to the same exercise. I believe I'm done with my plan. Let's, oh no, one little thing. In one of the postulates, there will be a statement that when practicing Schrodinger equation, one formulates total energy in the same way as one would do it before quantum theory, but for each symbol corresponding to physical observable, like velocity, position, momentum, magnetic field, electric field, angular momentum, one needs to put operators. Same as we did before, like for momentum along x, it's like this derivative is constant. And there is a longer list of three-dimensional momentum for kinetic energy in one dimension, three dimensions. So for angular momentum projections. And the one who will be either volunteer for the subject will just show this table. Maybe not volunteer, maybe everyone will select both subjects except this one, and this will be for the last one. So rush to make your choices. And through the course, we will slowly focus on each of them. And by the end of the course, this notations will look very natural and simple. Done for today. Have a nice weekend. Please consider to complete your choices now or by the end of today. And consider to start preparing slides. Although like 5 minutes is nothing, but weeks are busy and maybe it's smarter to prepare slides on the weekend. I would need your slides on Thursday midnight so that on Friday morning I'll upload everything to one computer and we'll go seamless. Yes, yes.
So for the postulates and the presentations, which ones should we start to create our first choice?
So let me look into the table.
So it looks like 1 through 6 is taken.
So I will take the first choices and then if there is, right now I'm too excited about the content, but like 1 or 2 hours after I will just calm down and finalize the list and distribute it.
Okay.
To let you know what to prepare. Okay, many thanks for participation. Wishing you a nice weekend. Meeting is done. I'll stay a couple of minutes slowly to close the files, and if there are more questions, ask or type. But meeting is done. Everyone is welcome to disconnect or depart physically. Thank you. Thank you.